Okay, let's talk about large language models. They're powering some of the most mind-blowing tech we've seen in, well, ever. But what's really going on behind the curtain?
I mean, it's a question we've all asked, right? You type a question into a chatbot and boom, this incredibly coherent, seemingly intelligent answer just appears. How does it do that? What's the magic trick?
Well, the best way to get your head around it is to imagine this. You stumble upon a movie script, but the last line is torn off. Your only job is to guess the next word. Once you guess it, you add it to the script, and then you have to guess the next word. And you just keep doing that over and over. Believe it or not, that's almost exactly what's happening every time you chat with an AI.
Yep, that's pretty much it. When you strip everything else away, a large language model, or LLM, is basically just a super sophisticated prediction machine. Its one and only goal is to predict the most likely next word for any given piece of text. It's not thinking like we do. It's just calculating probabilities on a massive scale.
So, to really unpack all of this, here's what we're going to do. First, we'll dig into that core idea, predicting the next word. Then we'll look at how on earth it learns to do that. After that, we'll touch on the breakthrough tech that made all this possible, the transformer. Then we'll see how you take that raw tech and turn it into a helpful assistant. And finally, we'll get to the really wild part, the emergent intelligence that comes out of this whole process.
All right, first up, how does this whole next word prediction thing actually work? It's all based on a loop, and it's simpler than you might think.
So here's the play-by-play. First, you give the model a prompt. The model then looks at that prompt and generates a massive list of every word it knows, assigning a probability score to each one. You know, what's the chance that this word comes next? Then it picks a word from that list, tacks it onto the end of your prompt, and, here's the key, feeds that new, slightly longer text right back into itself. It just repeats this process word by word until it's generated a full response.
Okay, but you've probably noticed you can ask the same question twice and get different answers. Why is that? Well, it's because the model doesn't always pick the number one most likely word. It injects a little bit of randomness, sometimes picking the second or third or even 10th most likely word. And that's actually super important. It's what makes the output feel more natural and creative, not just like a deterministic robotic calculator.
So that brings up the big question, right? How does the model even know what words are probable? How does it build that intuition? Well, that's where the learning part of machine learning comes in, and it all starts with a mind-boggling amount of data.
Think about it. To get really, really good at predicting the next word in any sentence, you need to have seen, well, pretty much all the sentences. So that's what we do. We basically feed the model a huge chunk of the internet. We're talking books, articles, websites, forums, the whole shebang.
And just to give you an idea of the scale we're talking about, if you tried to read all the text that just one model, GPT-3, was trained on, reading 24 hours a day, 7 days a week, it would take you more than 2,600 years. No joke. And the newer models, they're trained on even more.
So inside the model's brain, you can think of it as having billions and billions of tiny little knobs or dials. These are called parameters. The entire training process is just about figuring out how to tune every single one of those billions of dials. If you can get them all set just right, the model becomes incredibly good at that one simple task, predicting the next word.
So here's the training process in a nutshell. You start with all those billions of parameters set to random, so the model's output is just total gibberish. Then you grab a sentence from your training data, let's say, the cat sat on the mat. You feed the model everything but the last word, so the cat sat on the. You ask it to predict the next word. Of course, it'll get it wrong, but then you compare its guess to the actual right answer, which is mat. You then use this really clever algorithm to go back and slightly adjust all of those billions of parameters to make the correct answer, mat, just a little bit more likely next time. And then you just repeat that process, trillions of times.
The amount of raw number crunching this takes is, well, it's just staggering. I mean, get this. If you could do 1 billion calculations every single second, it would still take you over 100 million years to do the math required to train one of these big models. It's an absolutely astronomical amount of computation.
So how is that even possible? How can we do 100 million years of math in just a few months? Well, it's only possible because of a really huge breakthrough in AI that happened a few years ago.
See, the older models had a big problem. They had to process text one word at a time, in a sequence, which, as you can imagine, is super slow. But then, in 2017, a new architecture called the transformer came along, and it completely changed the game. Instead of reading word by word, a transformer can basically soak in the entire sentence all at once. It processes it in parallel. And this was the key that unlocked the ability to use modern computer hardware to train these enormous models.
And the secret ingredient, the real magic inside the transformer, is a mechanism called attention. It's basically a way for the model to figure out which words in a sentence are the most important and how they relate to each other.
You can almost think of attention as allowing all the words in a sentence to talk to each other to figure out the real context. So, take a word like bank. Does it mean a place you put money or the side of a river? Well, by paying attention to the other words in the sentence like water or cash, the model can understand the correct meaning. It's all about context.
Okay, so we've got this incredibly powerful text prediction engine trained on the internet. But that doesn't automatically make it a useful chatbot, right? In fact, it just makes it good at mimicking internet text, which can be weird or unhelpful. So there's a whole other crucial step to turn this raw model into the helpful assistant we actually want to use.
And this is where we move from what's called pre-training to fine-tuning. Think of it like this. Pre-training is like going to the library and reading every single book to just absorb the patterns of language. The goal is just to learn how to autocomplete text. But fine-tuning is like going to a finishing school. The goal here is totally different. It's to learn how to be a helpful and harmless AI assistant, using a much smaller, hand-picked set of examples and human feedback.
A really popular way to do this fine-tuning is with a technique called reinforcement learning with human feedback, or RLHF for short. And it's pretty much what it sounds like. Real humans look at the AI's answers and rank them. They give a thumbs up to the good ones and a thumbs down to the bad ones. The model then takes all of that feedback and uses it to tweak its parameters even more, learning what kind of answers humans actually prefer.
So, when you put it all together, you take this colossal amount of data, you run trillions of calculations on it using this revolutionary transformer architecture, and then you polish it with human feedback, something amazing and kind of unexpected happens.
You see, no one ever sat down and explicitly programmed the model on how to write Python code, or how to translate between French and Japanese, or how to explain quantum physics. Those skills just appeared. They are an emergent phenomenon. They bubble up naturally from that one simple task, predicting the next word, once you do it at an absolutely ridiculous scale.
And this is what leads to one of the biggest mysteries in AI today. Because these abilities aren't programmed in, but emerge from billions of tiny adjustments, the models are basically black boxes. We can see the input, and we can see the output, and we know the output is often really good. But it is incredibly challenging to peer inside and know exactly why it chose to write a particular sentence or make a specific prediction.
So there you have it. What started as a deceptively simple goal, just predict the next word, has, through sheer scale and clever engineering, blossomed into a tool with these complex, surprising, emergent capabilities. And it really leaves you with a big question, doesn't it? As we make these models even bigger and train them on even more data, what happens when this emergent intelligence gets even better?